Welcome and hello. This is a video tutorial in HEC HMS, and in this lesson, we're going to be discussing erosion and sediment transport, giving an overview and then discussing the different methods for subbasins. All right, what I have on the screen here is the HMS User's Manual. I'll leave a link to this page in the description, but what I first want to do is go to HMS directly and create a project. All right, that way I can go ahead and describe what I'm talking about from the User's Manual. So I'll call this, give your project a name, and then click on the folder icon to navigate where you want to save, and then click create. Okay, and then the only thing I really need to do here is create a basin model and then one subbasin. So I'll click new basin, and then let's open that basin up here in the model manager, and we're good. By default, the sediment or the erosion module within HMS is set to no. But if we click on the basin here in the Watershed Explorer, then down in the components editor, we can just select sediment, select that no, change it to a yes, and then click save. When we do this, we get this new sediment tab here in the components editor. And then when we click that, we've got a number of different options to select, starting with the transport potential. Transport potential specifies which method to use to calculate the stream flow sediment carrying capacity for non-cohesive sediments. So there's a number of different options here, and the user's manual has a link to the HEC technical reference manual, but I'm just going to go ahead and select one, but you can read up more on those if you want. There's also a cohesive potential here, which you can select. Then you'd have to also provide some data for that. Okay, I'm going to set that to none though. Below that, we have specific gravity and unit weights. So there are some default values just set right here, but go ahead and update these values for specific gravity and then the unit weight of clay, silt, and sand in units of pounds per cubic feet for the soils that are found in your basin. Below that is the fall velocity, and this is a required field. Fall velocity, sometimes known as settling velocity, refers to the rate at which a sediment particle sinks through a fluid, typically water. And the user's manual also has a link to the HEC technical reference manual for more information on these different fall velocity methods. And there's also a hindered settling velocity as well. At the bottom here, we have the grade scale. The first option is clay, silt, sand, and gravel. The second is AGU 20. So clay, silt, sand, and gravel is the default. And when selected, only 4 size classifications are used, but AGU 20 uses 20 different size classifications for erosion. In HMS, the erosion, deposition, settling velocities, and transport processes are computed differently for each size, either 4 different sizes or 20 different sizes. The user's manual also mentions if I go up to the transport potential and then I select sediment delivery ratio, which is this one right here, then I would have to input the different ratios for these different sizes of material: clay, silt, sand, and gravel. And if I do that, I'll say 1.2, 1, 0.8, and 0.6. These ratios represent whether or not that particular size of soil is going to be eroded or deposited. So if the number is greater than 1, then that particular soil size will be eroded. If it's 1, it's in equilibrium, it won't erode or be deposited. And if the value is less than 1, then it will be deposited. All right, so that's it for the basin model. Next, I'm going to add a subbasin to the model. Then we can check out the different erosion methods for a subbasin. So I'm going to click on my create subbasin tool, click to create subbasin 1. Okay, there it is. We'll go ahead and select that subbasin 1 now, which is in my basin. And I have an erosion method right here. This erosion method will only appear if in the basin model you have sediment selected to yes. So you need to change sediment to yes. And then for all the subbasins, you're going to have a erosion method to select right here. So we're going to talk about these in just a moment. But before we do, I should also point out that now in this options tab for the subbasin, we have an observed sediment time series dataset, which we can use for calibration. Currently, there are no time series datasets. You saw me create this project, and I haven't created any time series datasets yet. So let's go ahead and just do that real quick. I'll go up to Components, Time Series Data Manager, and I want to select Sediment load gauges. There it is, new. I'll just call this sediment 1 and then create. And I'll close that. And now I can select that sediment 1 time series data set. I'm not going to go into the details about how to add data to that time series data set, but you'd go ahead and select it and then specify either a manual entry or a DSS file. All right, back to the subbasin. Click the subbasin. And then for this erosion method, you can see we have a number of different options here. And regardless of which option we choose, we get this new erosion tab in the components editor with a number of different parameters we need to specify. So I'm going to, for the remainder of this lesson, talk about these different parameters specific to the erosion method that we select for the subbasin. The first one I selected is called Buildup Wash Off right down here. So I'll click on the erosion tab. And this particular erosion method, it was designed for urban environments that involve street sweeping. So not your forest land, not your agricultural land, but for urban environments. The initial time in days refers to the number of days since the last street sweeping or removal of sediment occurred. So I'll just say 0. Half time in days refers to the number of days required for half of the maximum solids to accumulate in the street curb under continuously dry conditions. Max solids right here is in pounds per mile. This refers to the maximum of accumulated sediment in the street curb under continuously dry conditions. The density in feet per acre represents the total length of street curb per acre of the subbasin. So these units right here are in English units, like pounds, miles, feet, and acres, and so on. If you're using metric, it would be different. But I just put 100 as an example, and that means if I have a subbasin that is 1 acre large and it has 100 feet of curb face, then that's 100 is what you would use. The sweeping percentage is the percentage of curb length that gets swept. So we'll say 90%. The sweeping efficiency percentage is the efficiency of the sweeping equipment to remove the sediment. I'll say that's 50%. And then days in intervals represents the number of days between scheduled sweeping operations. And then a couple more here. Coefficient here in 1/inches deals with how quickly sediment is removed during a storm event. I'll just put a 6. And then the last two is exponent and gradation curve. The exponent is used to distribute the sediment load into a time series sedograph. A small exponent flattens the sedograph compared to the hydrograph, and then a large exponent heightens the sedograph compared to the hydrograph. I'll put 0.75 there. And then the last one is the gradation curve. Sorry, there's a lot of reading in this lesson, but the gradation curve is the grain size distribution curve. So we get a general feel of what is the particle size distribution of the soil for that selected subbasin. This is a paired data set, and typically I see a paired data set icon over to the right, but I don't see it here. So let's go ahead and just create it and make sure that it works. I'll go up to Components, Paired Data Manager, and then the one I want to select is Diameter Percentage Functions. I think, let's see if this works. So I'll call this Grain Size Distribution 1, and then Create for Subbasin 1. And then now I can go ahead and make that selection. We can also add data to that diameter percentage function right here. Select it, and then like for manual entry, we would type in the diameter and then the percent finer. Classic. And that concludes the different parameters we would use for our build up and wash off erosion method. All right, back to the subbasin. Let's select the next one, modified USLE. I'm going to go in order here of the user's manual. This refers to the USLE is Universal Soil Loss Equation. This method works best in agricultural environments. If I click on the erosion tab here, we have a new set of parameters. Some of these parameter values are new and then some are the same. So I'm really only going to describe what we haven't already described from parameters from other methods. All right, so erodibility factor here is a new one for us. This describes the difficulty of eroding the soil. So I'll put 0.38. Now, typical range for this would be a small number would be 0.05 for unconsolidated sands. And then maximum value would be closer to 0.75 for well-consolidated silts and clays. The topographic factor right here refers to the susceptibility of erosion due to length and slope. A minimum value here would be 0.1 for short, flat slopes, which don't erode much. And then a maximum value would be 10 for longer, steeper slopes, which are much more susceptible to erosion. Cover factor is next. This describes the influence of plant coverage on erosion. So, for instance, the more plant coverage, the less likely that the subbasin will erode during a storm event. A small value here would be 0.0001, and that would be for like a foresty environment, forest soils under a dense tree canopy. And then a maximum value of high erosion would be bare ground, that would be 1. And then a middle value would be fully mulched land cover, but no tree cover, and that would be about 0.1. Okay, next up is a practice factor. I'm going to put 1. This refers to soil-specific conservation practices, and the user's manual does provide more information on what this value means. Threshold, CFS, exponent, and gradation curve were all parameters covered in previous erosion methods. All right, so I'm going to go back to the Subbasin tab here, and the next one I'm going to select is LA Debris Method EQ1. And then I'll click on the Erosion tab, and now we have some new parameters to discuss. The first one is this AT factor 1.0. I should probably first mention that the LA Debris Method EQ1 is an erosion method that's used for arid or semi-arid regions near Southern California, or similar to regions near Southern California where this method was developed. And this particular EQ1 method was meant for small watersheds, very small, like 0.1 square miles up to 3 square miles. All right, so let's go back to that erosion tab here. AT factor is the adjustment transposition factor. It describes the difference in geomorphography between the subject watershed and the San Gabriel Mountain watershed where this particular method was developed. So the value here would be 1 if the subject watersheds, the basin 1 here, had a similar geomorphography to the San Gabriel Mountain watershed. However, if my subbasin 1 exhibited more erosive potential, then the value would be greater than 1. And if there was less erosion potential, it would be less than 1. Next up is the relief ratio. So this is in feet per mile. This is the slope of the longest stream in units of feet per mile or meters per kilometer if you're using metric units. So just be careful about the units there. Next is the fire factor method. So what we have here are 2 options. There's user specified fire factor and Pock and Lee fire factor. If I select user specified fire factor, I then have to specify what that fire factor is. Now the fire factor can range from 3 up to 6.5. So I'll just say 5. But a small value like 3 would be if there was no fire in this subbasin for more than 10 years. And I would use a large number like 6.5 if there was 100% coverage of a recent wildfire in less than 1 year. The other fire factor method is Pock and Lee. And in this situation, I would enter the date in this particular format of the last wildfire and then the percentage of the subbasin that burned during that last wildfire. The flow rate threshold, again, refers to that threshold of flow rate that causes erosion. So if the precipitation event causes a flow rate that is greater than the threshold, then erosion occurs. If not, erosion doesn't occur. I already talked about that. And then, of course, exponent and the gradation curve have also been described in previous erosion methods. All right, back to the subbasin tab. The erosion method, LA debris method, EQ 2 through 5, is basically the same as EQ1, but the difference is this was developed for larger watersheds. So I mentioned EQ1 was for very small watersheds in that arid/semi-arid environment, and that is for very small watersheds at most 3 miles squared. EQ2 through 5 refers to watersheds that are from 3 miles squared up to 200 miles squared. So if I click on the erosion tab here, we have the exact same parameters that we just saw with the EQ1. All right, so back to the Subbasin tab. Next up is a multi-sequence debris prediction method right here. So I'm going to click on the erosion tab here. And now we have a few new parameters and a few old ones. AT factor, we already talked about that. Relief ratio, already covered. Okay, next up is this maximum 1 hour rainfall intensity in inches per hour. So I'm going to say that's 0 0.1. This is sometimes abbreviated TMRI. This intensity is used to identify which rainfall events are strong enough to mobilize sediment by exceeding a critical energy needed for sediment entrainment. The next one down is the total minimum rainfall amount in inches from a storm event. I'm just going to type in 0 0.3. This is in inches, so it's a depth. This is sometimes referred to as abbreviated TMRA, and this refers to the minimum rainfall depth of a storm event required to transport the sediment to the concentration point. So the TMRI is about causing the erosion, and then the TMRA is about transporting that eroded material. Okay, after that, we have the fire factor method. We already talked about that. Threshold, flow rate, exponent, and gradation curve. Okay, back to our subbasin. Next up for our erosion method for the subbasin is the USGS long-term debris model. I'll click erosion here. And then what I want to specify is the relief. This time the relief is just in feet. So this is the maximum elevation of the subbasin minus the minimum elevation of the subbasin. So I'll just say 2,000 feet. And then date, this refers to the date of the last wildfire. So you just type in a date using that particular format. And then the burn area in miles squared. This is just as it sounds. It's the area that last wildfire burned. Not necessarily the entire watershed, but whatever that area is. And then the flow rate threshold, exponent, and gradation curve. We've already talked about those. All right, we have a couple more, I believe. Next is USGS Emergency Assessment Debris Model. So let's go ahead and select that and then click on the erosion tab. This one is just like the other USGS method. The only difference is we don't have to specify the wildfire date. So we still have the same relief and the burn area, but if you don't know the date, this is probably the one to use. Threshold, exponent, and gradation curve, same as before. All right, I think we have one more method to discuss, 2D sediment transport right there. Okay, I'll click on the erosion tab. What we have for parameters here are all new except gradation curve, and they're set at 1.0 for default because these are all scaling factors that can be used for calibration. The first one is the total load scaling factor, and it would typically range between 0.2 and 5.0. It's used to scale the total load of sediment transport. So that would definitely be used for calibration. Next one down is the critical mobility scaling factor. Again, our default value is 1.0. It would range between 0.5 and 2.0. A value less than 1 would pertain to reduced mobility of the eroded material, and a value greater than 1 would refer to increased mobility. This sheet and splash erodibility coefficient, I'm just going to go ahead and also type in 1.0. The range is between 0.5 and 1.0 based on soil type and land cover. This is the parameter used to calculate erosion from sheet and splash flow on dry land with runoff. The next parameter is the sediment total roughness factor, 1.0. This is going to also range from 0.5 to 1.0, and this factor accounts for grain transport and bed form roughness in sediment transport calculations. The adaptation coefficient also is set to 1.0 by default. This can range between 0.5 and 2.0, and this coefficient is used in non-cohesive sediment transport calculations, and it calibrates sediment transport based on the total load adaptation length. All right, and then lastly, we have the gradation curve, which we already talked about, and that is it for our different subbasin erosion material parameter descriptions. That's going to be it for this lesson. What we did was we created a basin. We selected yes for our sediment, which gave us some parameter data to set up here in the sediment tab. Then we created a subbasin and then selected the different erosion methods and talked about the different parameters for each method in this erosion tab here using HMS.